So hi everyone, welcome back to another episode of the Rocket Media. Today I am with one of the legendary god physicists of India, who is a recipient of Direct Medal and Breakthrough Prize in Fundamental Physics, and he is a fellow of Royal Society and a Padma Bhushan awardee. I am talking about none other than Professor Ashoke Sen. Swagata sir, so glad to sit in front of you.
Sure.
So, talking about you, you grew up in Kolkata, and your father was a physics professor at Scottish Church College. So, tell us about early interaction with science and physics, like how physics came up in your life.
I think physics came up in my life more by random walk. I mean, in school, I was interested in mathematics, but not. I was not a particularly good student. I was being a good student, but not one of the top students, right? And probably the main reason I would say that I went into physics, is because that was the thing to do at that time. So if you get admission into physics in a good college, you go there, right? That used to be the norm.
So, what kind of intellectual environment shaped you? There is a meme famous on X, we have many legendary professors from Bengal. So, what kind of environment that you had in your childhood and that intellectual environment that shaped you?
I mean, we all knew about S.N. Bose and M.N. Saha, for example. Right. I mean, not just the ones who are in physics, but everybody knew about them, right? So that certainly made science one of the top things to do at that time. Right.
And if I can ask you a very fundamental question, like talking about physics and mathematics. So you always wanted to become a scientist, but you didn't had that idea of what is science very early on in your life. So what is physics and how physics is different from mathematics and how mathematics support physics. In one of your interviews, you said keep any day keyword abundant string theory if you find any mathematical inconsistency. So if you can talk about physics, mathematics, and how these are different from each other.
Yeah, so I started getting really interested in theoretical physics, I think probably when I was in IIT Kanpur doing my masters.
Right.
Before that, I really didn't have much idea, but there I took more advanced courses and I decided that I'll go into particle physics, general relativity kind of thing. And then, of course, in that process, I also learned that mathematics is really the language of physics. That if you are trying to build a theory, right? The first thing you should test is that it's mathematically consistent. It's just not just enough to say that, okay, this is my theory, right? Without having some equations behind it.
Right.
And that, I think, is a universally accepted fact. I mean, why mathematics is so powerful, one doesn't know, right? But everything seems to be following the laws of mathematics, right? I mean, if there is any law at all in nature, it should be, mathematically consistent.
Right.
And that's also the same principle that I said in this interview that you are mentioning, that in string theory it becomes even more prominent because in string theory we don't understand the full structure of the theory, right? But we know of many different ways of studying the theory, right? And these different ways of studying the theory typically gives different looking answers,
right,
for the same physical quantities. And then it's a highly non-trivial fact that actually those answers which look different are the same, right? And this way it has come up with many new identities in mathematics itself, which were not known to the mathematicians. And then they proved it after string theory found that two different ways of calculating something gave apparently different answers, right? And so that's the kind of consistency that one is demanding. Right? If you have a theory which is formulated from the beginning, right, in a fully consistent way, then of course it's guaranteed that it will be fully mathematically consistent. Right? String theory is not quite like that, right? Because there are many different formulations which look completely different. Nevertheless, they seem to be all consistent with each other.
Right. We will talk about string theory in detail, but just talking about fundamental things apart from these equations and theories. What you used to question basic things in life, talking about cosmos and formation of universe, these kind of stuffs in your college days.
Yeah, meaning cosmology was of course a fascinating subject, but as I said, I didn't really have much idea about this distinction between what is that which field is for what, right? I mean, of course, you look at the sky, right? That's a fascinating object. But what part of physics actually deals with that, I certainly didn't have any idea.
Right.
So those things really become apparent only later in my life.
Okay, and talking about talking just further into this, you have very diverse experience of working into different fields or different domains. So how do you view this origin of and expansion of universe, like talking about Big Bang? Was it really beginning of everything, space, matter, and time, or was it simply a point, up to which our current theories work and describe the universe?
Yeah, right now we know that our current theories work up to that point, right?
Okay.
Beyond that, we don't know.
Okay.
Right? In principle, once you have a complete understanding of the theory of nature, we should be able to know, right, what happened, so that it's even meaningful to ask what happened before that point, or maybe that's where everything began.
Right. And we often hear that one more thing, universe is not just expanding, but expanding at an accelerating rate. So how do we know that? And what is driving this expansion?
Yeah, so the way we know that is through experiments.
Okay.
Right? Of course, when the acceleration that the universe is undergoing is so slow that we will not feel it the way we normally measure acceleration, right? But what people do is that they look at distant stars, right? And from there you can estimate the distance, right? The speed at which you are moving away from us. And using all those informations, you reconstruct what the early history of the universe was. Because the farther we look, the earlier the state of the universe we are looking at, right? Because it takes time to travel from far away objects to us. Okay, so that's the way you know how the universe was in the past, right? Because by looking at farther and farther away objects, and once you know the full history, right, or part of the history, then you can check what the acceleration is, right? How much the universe has expanded in with different different epochs of time.
Right. So physics and science is mostly about observing things and just giving your laws and those stuffs.
Exactly. Yeah.
Right.
I mean, in this case, it's not that you have to devise new laws. The laws are just Einstein's equations. So you have not needed anything beyond Einstein's equations, right? But it's a question of what kind of sources of energy there are in the universe.
Yes, sir.
Right? And this acceleration is now explained by what is called the cosmological constant or dark energy. That's a particular kind of source of gravity that one needs to explain acceleration.
So something like dark energy is driving this expansion. So people often confuse, they are unable to differentiate between dark matter and dark energy. So could you please explain both these terms and to us?
Yeah, so dark matter is like ordinary matter.
Okay.
Right? I mean, if, for example, if there is an explosion in a normal explosion,
right,
things will fly apart. Right, but as they are flying apart, their gravitational pull will try to pull them together, okay? And so one expects that the speed will slow down, right? So the expansion will slow down, and the universe is also like that. That if you have an expanding universe, right, it's expanding because initially there is a burst, but as the universe expands, the matter will try to make the expansion slower and slower.
Because of gravity?
Because of gravity.
Okay.
The standard gravity, like just all matter is pulling them together. Pulling. It's like if you throw a ball, right? Then the speed of the ball will slow down from the earth, right? Maybe you throw it so hard that it escapes, but nevertheless, the fact that it slows down as it moves, that remains, right? That's what ordinary matter behaves like.
Right.
So dark matter is like that, just like ordinary matter. Okay? But that cannot explain why the universe is accelerating, right? Because it's opposite of what the matter will do.
Right.
Right. And dark energy is a special kind of source of energy which actually causes the acceleration.
Right. And if we just go back to that Big Bang theory again, so I want to bring in a little philosophical and civilizational angle. Like Nobel laureate mathematical physicist Sir Roger Penrose proposed that Big Bang was end of previous universe, and rather than starting off something new. So he called this a theory conformal cyclic cosmology. So how do you perceive that statement, given that talking about our civilization, West has seen time as linear, but our civilization has seen something cyclical. So how do you see that?
Well, I don't know about our civilization, but the cyclic universe idea, I think, has some specific predictions.
Okay.
Right? He himself tried to identify some patterns in the sky in the microwave background, which he thought support cyclic universe. But as far as I know, that has not really succeeded. I mean, it's not consistent with what. So far, there's no experimental evidence that something like that happened.
Like even also like Stephen Hawking also talk about that like Big Bang occurred at t equal to 0. Like hence God had no time to before it to create the universe. Like hence God doesn't exist. But I don't know want to know about existence of God. But if we consider time to be like cyclical, so that argument still holds. Like ki Big Bang like started at t equal to 0 and
Well,
that
the point is if to see if there is anything beyond before the Big Bang, right?
Right.
One is to first understand the singularity. If it's really singular, of course, there cannot be anything before that because that's where things end. But one expects that maybe once you understand the very short distance properties of matter very well, the singularity will be resolved, and then we will be able to, in principle, answer this question.
okay.
Otherwise, it just remains speculation, right? Whether the universe began at t equal to 0 or whether there is something before t equal to 0, till we can understand how to resolve the singularity that we have in our current theory, right? We cannot really answer any of these questions.
Right, and I want to talk something about like later point of time, like ki how string theory like can explain these stuffs. But before that, like talking about time. So what is time in physics? Like is time an emergent phenomena? Like why does it seem to move forward? Like just from past to future.
Yeah, so far I think we don't understand time as an emergent phenomenon, right? There are many examples where space has emerged, right? There's some space directions, one emerges from some dynamical considerations. But so far there is no evidence that time is emergent, right? Although many people believe that maybe eventually we'll understand time also as an emergent phenomenon.
So where does this arrow come from? Like is it come from entropy or which phenomena? Like this arrow from like past to future.
In a sense, I would say it's initial condition.
Okay.
Right? Entropy, of course, increases, but even in the vacuum, right, there is a sense of time, even if there is nothing where there is no entropy. But it's more like, in our universe, it's like an initial condition, right? I mean, like,
right. So there is
time asymmetry.
Right. So there is very nuanced question like, is theoretically possible to reverse time? Like in a highly controlled setting, you can stop a simple microscopic system. But when we like, talk about macroscopic system, like, technologically it's impossible due to chaos and infinite precision. So is it theoretically possible?
Well, it depends on whatever theory. Theoretically, it is possible because the laws, as far as they are time reversal invariant. Okay, at least to a large extent. And so in principle, you can set up an initial condition where it gets reversed, right? The function of the universe starts moving in the reverse direction, right? But certainly it doesn't look like it's technologically possible, right? I mean, nobody has proposed any scheme for doing that.
Right. And what are your opinions about like, ki multiverse or parallel timelines, if you have any theory about that?
Well, parallel timelines, I don't know. I mean, there is a notion of this many world interpretation of quantum mechanics.
Okay.
Right, which basically says that at every stage, the world is splitting apart into many copies and different. Quantum mechanics is probabilistic, right? And the idea is that the different worlds, right, realize different outcomes with appropriate probability. But that's basically just an interpretation, right? I mean, I don't see that there is anything. That's any different from the standard interpretation of quantum mechanics, the Copenhagen interpretation, the probabilistic interpretation. You don't try to go any further.
Right.
But there's another notion of multiverse, which is that our universe itself, right, may have different regions in different, where different, I'll not say different physical laws, but the way the nature is realized is different in these different regions. That could still happen, right? We don't know enough about our universe to rule that out. The different parts of our universe are in different states.
And but when many physicists talk about this multiverse thing, so what do they actually mean? Like, is it a very serious scientific possibility, a mathematical consequence of some theories, or like, just a speculative idea if we go deeper into this?
Well, it's certainly mathematically possible.
Okay.
Right? Whether it's physically possible, you don't know. Right? I mean, for example, even if you're in our universe, right? I mean, if you look at the we can see right now about light coming from about 45 billion light years away. Okay? But today, if we start send a spaceship, it can reach at most 10 billion light years.
Okay.
So, if in some region of the universe, right, which are beyond these 10 billion light years, something was happening, we wouldn't know, right? So it is in principle possible that those regions of the universe, right, which are out of contact, right, they have become something else, right? They have gone into a different state, right, which we'll never be able to see. So in that sense, the concept of multiverse is very much physical, that it can happen, right? Whether it actually happens in our universe, we don't know. Right? That requires a much better understanding of the theory that describes us. Right? Not that it is not knowable, right? At least probabilistically, we can calculate in principle if we know the theory very well. Right? But right now, our theory is not powerful enough to make such predictions.
And can string theory tell us something deeper about time, Big Bang, and multiverse thing? Because it's a very prior candidate of theory of everything. So
about time. So far, it hasn't had anything new to say, because string theory is formulated exactly in the same way as other quantum theories, where time, you start with a notion of time, right? Multiverse, yes, certainly string theory has solutions, right, where the universe, there are different states of the universe, right, and it is certainly possible that different parts of the universe are in these different states.
Right.
It's like, to just give an analogy, if you have a big reservoir of water, right, you can imagine that some part of the water is in ice, stays as ice, some part stays as steam, some other part stays as water, right? And a person living inside ice will feel very different thing from a person living inside water and living inside steam. So multiverse is a more elaborate version of this, right? That the different parts of the universe are in different states, right? And it can certainly happen.
Right, and can you please, talking about string theory itself, can you please tell us about string theory for the layman understanding? So, initially it started in 1960s, as a way to understand hadrons. So, can you tell us about string theory for the layman and, how it is theory of everything?
Yeah, so in the 1960s, when string theory started, it was proposed as a theory to understand strong interactions, right? How the protons and neutrons and other strongly interacting particles can be explained, because the usual tools were not enough to explain those. Right. But then, by the early 70s, people understood that just normal theory of point particles is enough to explain hadronic physics. Right? Something called quantum chromodynamics came up, and that was enough for hadronic physics. But then, within a few years, people found that while string theory is not good enough for, not needed for hadronic physics, it actually has a very specific feature that one of the states of the string mediates gravitational force. And gravity was very hard to understand from the usual quantum perspective, in the usual parts of quantum field theory.
Right.
And so that's the time when people first started thinking about string theory, not as a theory of some one particular force, but as a theory of all forces, but at a much more fundamental level. Okay? Because nothing else was able to accommodate gravity at that time.
Right. So in one of your lectures at ICTS, I think you gave a very beautiful analogy about string theory, comparing it to a single room, viewed through 5 different windows. And in early days, physicists don't realize, they were looking into the same room. If we talk about classical mechanics or quantum mechanics, so can you please throw some light on that statement and this analogy?
Yeah, so basically in string theory, the basic idea is that elementary constituents of matter are not particles. That's what the conventional view is that elementary constituents of matter are particles. Like electron is a particle.
Right.
Then neutrino is a particle. Photon is a particle. In string theory, the idea is that the elementary constituents are actually one-dimensional objects, like strings.
Okay.
But a one-dimensional object can exist in many different states of vibration. Right? It can vibrate, but it can vibrate in different harmonics, for example, or it can vibrate in different amplitudes. Sometimes the vibration can be big, sometimes it's small. And what one finds is that when one puts it in the quantum theory, these different vibrational states of the string behave as if they are particle-like objects. Okay, at least at the kind of length scale that we can probe today, they will all appear as particles. Okay, and so then the idea in string theory is that each of the different elementary particles that we see are all different vibrational states of the string. Okay, so that was the basic idea of string theory. And then people tried to understand the theory in detail, and then they found that it's very constrained, that you cannot just change the rules arbitrarily. Okay? And people came up with 5 different sets of rules that we can have for these strings, and those are called the 5 different string theories, consistent string theories. So that was good because we could reduce the number of theories, right? But it was still somewhat unsatisfactory in the sense that, I mean, if we are trying to find a theory of nature, right, then who decides which of those 5 theories should describe nature?
Right.
Right, and then later it was realized that actually those 5, what people thought are those 5 different theories, are the same theory, right? There are different ways of looking at the same theory. And this is what I was telling you earlier, that I mean, the reason that people didn't realize that they are the part of the same theory is that when you actually calculate some physical quantity out of those theories, they look different. Okay? And it's only when you compare them in detail and use various powerful mathematical identities that you find that they are actually the same.
Right. So, like, this is very interesting, but like, when we look at everything, like from a outer perspective or landscape, like, talking about string theory, as you mentioned, like, at most fundamental level, everything is like, made of tiny vibrating strings, right? But like, every experiment that we have seen or we have read in our early textbooks, like, it seems to detect particles. So like, why do we believe in strings at all? What is the actual evidence without any mathematical backing or?
Okay, yeah. So first of all, the fact that we see the constituents as particles, that's not inconsistent with string theory, because in string theory you can also estimate what should be the sizes of those particles, right, of the string.
Mm-hmm.
Okay, and you find that those are actually extremely tiny, like 10 to the minus 33 centimeter.
Okay.
And whereas today the accelerators probe a distance of 10 to the minus 17 centimeter. So there is no way that the accelerators will see the string structure. Okay, so that's the reason why string theory is not directly in conflict with what we see in experiment. But you can nevertheless ask that why do we believe in string theory, right?
Right.
And the main reason is that string theory seems to be the only theory which can accommodate gravity, okay, and possibly other forces, right? What one finds in string theory is that string theory automatically has gravity, whereas it's very, very difficult to have any other quantum theory which contains gravity.
Right. And what is this, like, central problem of quantum gravity? How does, like, it fix the quantum gravity problem? If you can briefly talk about that too. You mentioned it earlier too.
Yeah. So in quantum gravity, the main problem is that if you take 2 electrons,
Okay.
and ask that if you throw in 2 electrons at some energy, what is the probability that they'll come out at 30-degree angle, right?
Okay.
And this you can calculate in quantum field theory, okay, which is a standard tool that one uses for describing theories of elementary particles, and you get some finite answer. Okay. But if you now include the effect of gravitational force, right? The gravitational force is very tiny. Okay, that's why one normally ignores gravitational force. But suppose you say, okay, let's try to calculate what the gravitational force gives.
Mm-hmm.
What one finds that it gives a very, very tiny number times infinity. So anything multiplied by infinity is still infinity, right? Even though if it's tiny. And that's the problem with quantum gravity, that while one expects that the gravitational force should be very small, right? If you actually try to include its effect in a quantum theory, you find that it gives divergent answers, infinite answers, which are certainly not sensible answers, right? Because a physical quantity cannot have infinite answer.
Right. So
This is a problem with quantum gravity. And one can identify the source of this problem because when gravitational force is proportional to the masses of these objects, right? And now if you combine this with the theory of relativity, which basically tells us that if you have a very fast moving particle, then it behaves as if its mass has increased, right? Because this E equal to mc square, Einstein's formula. So now imagine that the 2 electrons are moving very fast.
Mm-hmm.
Okay? Then effectively their masses have increased. Okay? And so the gravitational force between them also increases.
Right.
So this increase in gravitational force with the energy of the electron is what is responsible for these infinities that I mentioned. Okay. In string theory, what happens is that it is true that the gravitational force still increases with energy, okay? But now the energy is not concentrated at a point, it's spread out over the string.
Right.
And that is sufficient to make this into a finite quantity. Right? And that's the way string theory avoids the problem of the standard problems that we encountered when we try to make a quantum theory of gravity.
Wow, explained it so beautifully. Like even I got to understand a lot of things. So talking about your work, like the work that you have done, you're famous for S-Duality. So can you first explain what duality means in physics? Like, is it like two completely different looking theories are actually describing the same reality, or first?
Yeah, duality is basically that two theories, right, which look different, right, can actually give the same physical
Okay.
theory, right? And duality perhaps is a somewhat limited word. Okay, this is it's called duality because initial examples all had two theories equivalent, but more generally there can be multiple theories which all describe, which are all equivalent in different ways. Okay. And so my work basically involved duality symmetries because in the early days, while there is the idea that such symmetries may be present, people didn't believe it very much, right? Because the evidence was very poor. And it was also not clear how to even test it. Because typically what happens when two theories which look different, okay, are supposed to be the same theory, then any quantity that you try to calculate, okay, if it's simple in one theory, it becomes complicated in the other theory. Right? But if you want to see if they're the same, you have to be able to calculate in both theories, right? And then check that they're the same. Right? If you can calculate it in one theory, but not calculate it in the other theory, then you have no way of saying that they are the same. Right? So my work was basically to try to identify some quantities that you can actually calculate from both sides.
Okay.
And then I check that when you are able to calculate things from both sides, they actually agree.
So you explained mathematically derived some results out of that.
That's right, yeah. Okay. That I provided examples where you can actually take two theories and show that things computed from the two theories are the same.
Can we go a little deeper into your work? Like, I want to understand more from you about this S-Duality thing. Like, what kind of things that you worked in it, what kind of quantities you derived or explained.
Yeah, so one of the things that, as I said that there are elementary particles, right? A given theory has some elementary particles. Okay, so you can calculate what kind of elementary particles a given theory has.
Okay.
Now let's look at a dual theory, right? If you look at the dual theory and look at what kind of elementary particles they have, they don't match. But the idea that you shouldn't compare elementary particles of one theory to elementary particles of the other theory. You should compare all particles of one theory to all particles of the other theory. Okay. So what I showed is that the elementary particles in one theory actually become bound states of more than one particle in the other theory. Okay. And then I actually calculated what kind of bound states you have in this theory and showed that they match. Once you include both the elementary particles and the bound states together, then the two theories have the same kind of particles.
Wow. After that, then came the Sen conjecture. So, the idea that open string tachyon condensation means unstable deep dense decay to nothing. So, you made a very precise prediction about energy released. So, and it was later confirmed mathematically too. So, what does it feel to make a prediction about something that no experiment can directly prove, and we have a mathematical proof of something? If you can talk about this.
It's like So again, it's like maybe I can go back to that. In the initial days, right, people had what are called bosonic string theory. And the bosonic string theory is also the standard string theory, except that they had some kind of particles whose mass seems to be imaginary, right? Or the mass square, right? Square of any number is a positive number.
Okay.
But it was negative number for those theories, right? And then people believe that those theories are not consistent. And still today we believe that those theories are probably not consistent.
Right.
In superstring theory, where these problems are not present, okay, one could still find configurations of other objects, okay, which have this kind of issue. That it has some, looks like it has some particles whose mass square is negative. Okay. But we understand in quantum field theory, right, that what a negative mass square means, right? It basically means that it's like imagine that you have a hill, just imagine that you have a hill,
Okay.
right, and some valleys, right, and you put a particle on top of the hill, okay, then that's an unstable position, right? A little push will make it roll down to this. And in quantum field theory, if when you have particles with negative mass square, it basically means that you have some field which you have put at the top of the hill, right? And that's why if you give it a little push, it will start rolling down.
Pullings.
In string theory, we had such objects, but there was a similar interpretation of what happens when you give it a push. Okay. And this conjecture basically was a conjecture about what happens when you give it a push, right? And that's what. So using this, I could calculate the difference between the height of the hill from the valley. Okay, there's a precise mathematical formula.
Okay.
And then that was later verified. That is indeed the case. We had first verified it, checked it numerically, but then there was an analytical proof that was given, right, of what happens when you come down to the bottom of the hill.
Wow.
And this, I mean, some people have also tried to make use of this in the early universe, right? That when in the early universe, right, maybe there are some field which are at the top of the hill, and it eventually rolled down.
Like in examples?
I mean, this is sometimes used in describing what is called the end of inflation.
Okay.
So the idea that the end of inflation is like you have two different kind of universes which are moving towards each other, right? And once they come close enough, then this extra valley develops, and then it starts rolling down, right? So the inflation is the part when these two universes are moving towards each other, and the end of inflation is when the valley develops and then the field starts rolling down.
Okay, great. And like, what would you like to say those like, critics of string theory, like, वो just make criticism like, कि like 50 साल हो गए अभी तक कुछ पता नहीं है कि सर क्या फंड का क्या होगा, क्या यूज होगा. So what would you like to say to them?
Yeah, so I would say that, okay, I mean, it's possible that string theory will not eventually give the correct theory of nature.
Okay.
But so far there is no alternative, right? It's not that there's an alternative of what is the correct theory of nature and we are not paying attention. Right? It looks like string theory is the best candidate. Okay? And right now, if all of us decide that, okay, since nothing has happened for 50 years, we just give up and not do anything, then maybe we'll never find. Okay, imagine that we do that, and string theory is the correct theory of the world, right? Then we'll never discover it. Okay? On the other possibilities, maybe it's not the correct theory of the world, okay? But some people continue working on it, right? The loss there is that maybe some people will waste their whole life working on a subject which is not correct.
Right.
But nevertheless, right, they have to do it because what if it is the correct theory of the world? So I would say that string theory is such that it's not that everybody should work on string theory, right? But there should be people who are trying to push this, because so far we have not discovered what is the correct theory of the world. And so far string theory has not turned out to be that there is no mathematical inconsistency in the theory itself, right? So given that this is the best candidate, right, some people have to work on it. Right. Otherwise, you may never find what the final theory of of nature is.
Right. You're a right advocate for the string theory, and I hope you win. So talking about this brings me to another important idea. Like if we talk about two terms, the landscape and the swampland. So can you please explain the difference between string landscape and this swampland?
Yeah, so the string landscape, okay, the word landscape came first. That what basically people found is that even though there is a unique string theory, right, it has many solutions.
Okay.
And these many solutions you can think of as different states of string theory. Just like as I was describing, if you take the theory of H2O molecules, right, there is only one theory of H2O molecules, right, the forces between water molecules.
Okay.
But that has many realizations, right? It can exist as ice, it can exist as water, it can exist as steam. So similarly, string theory has many different realizations. Okay, and those different realizations are what people call the landscape of string theory, right? That is like different realizations at different points on a landscape, right? And then the swampland, right, basically refers to those theories which look otherwise consistent, but they are not part of the string landscape, and they are in some sense inconsistent because that even though they look consistent, when you don't include gravity, once you include gravity, they become inconsistent.
Okay. And in future, like string theory can explain these things, maybe.
Yes, string theory can explain this thing in the sense that by definition, anything that comes from string theory is in the landscape,
Okay.
right? So in essence, there is nothing to explain. That swampland are things that cannot come from string theory,
Right.
right? And landscape involves the things that actually come from string.
So by definition, we define these two like that. This comes from string theory and this doesn't come
Exactly,
from string theory.
that's right.
Okay, and like talking about like black holes, which is one of the most fascinating topics like college students find these days. So why are black holes so useful for testing string theory? And you have treated them like a calculation tool, if I am not wrong. So you introduce entropy function formalism to count the microscopic state of black holes. So if you can talk about the black holes and like how they are natural laboratories for quantum theory.
Yeah, so the black holes are useful for quantum theory, are useful tools or laboratories, I would say, right? That because they have some unusual property that they are classical solutions of general relativity,
Okay.
but nevertheless they act as if they are thermodynamic objects, right? And they carry entropy. And this is very unusual. No other system has this property, that if you have a classical solution, it has no entropy typically, because it's just one state of the system. And then the challenge is to understand what this entropy means. Right?
Okay.
Because typically the entropy is related to how many different states the system has, right? For given some crude properties. Right?
Mm-hmm.
And as I said, in normal classical theory, once you have a solution, then that gives a state, right? So there's no entropy because there's only one state for that, right? Black hole seems to be different. So there is a precise calculation of the black hole entropy, right, which was done independent of string theory, just from classical general relativity. And then string theory actually produced examples where that result is obtained just from counting of states.
Okay.
That there you don't look at the geometry at all. You just take some quantum states, count it, and people found exactly that it matches what you got from the other side. And that gave one strong evidence, besides the fact that string theory makes quantum gravity finite. Okay? The fact that it could explain the black hole entropy gave a strong evidence that string theory actually is a genuine quantum theory of gravity that goes beyond what we call perturbation theory.
Mm-hmm. So, like, have you heard that joke? Like, a black hole comes to restaurant and restaurant owner says, like, we don't serve your kind here, and black hole says, "Don't worry, I consume everything." So, have you heard that joke?
No, I've not heard it.
And like, what are your thoughts on humanity capturing the first image of black hole? I think that happened like
I think it was very exciting because it actually proved. Okay, I think nobody. At least no practitioner in this field had doubts that black holes exist.
Okay.
But still, to see it, right, is different, right? That you can actually observe a black hole. So that was certainly very exciting.
Right, and someday that.
I mean, the same as gravitational waves, right? Nobody believed that gravitational waves don't exist, right?
Mm-hmm.
But it was not clear that we will ever be able to measure them, right? Because they are very weak. And the fact that we could measure gravitational waves, right, that was exciting. And it was also exciting because that meant that we can actually, we have a new tool to explore the universe.
Right. Someday that can happen for string theory too. Like, we can see some.
Yeah, certainly it can happen.
Right. So, like, for a normal person like us, like, why should we care a lot about this theoretical work? Like, does fundamental physics eventually create technology, or is it more about like, just understanding reality? So why we should care a lot about these stuffs?
Yeah. So certainly when scientists work, for most scientists, right, they don't care about applications, right?
Okay.
Nobody is currently working on string theory thinking that someday it will have application.
Okay.
But one can also say that about Einstein, right? Einstein never thought that his general relativity, for example, which was so esoteric that very few people understood it, right, can ever have any application.
Right.
But today, I mean, we know that without general relativity, the GPS system will not work, right? Because general relativity tells us that the clocks in the satellites move at a different rate compared to clocks on the ground. And since the GPS requires synchronizing the clocks on the ground to clocks in the satellite, you have to take that into account, that clocks in the satellite have different rate of movement, that they measure a slightly different time compared to people clocks on the ground. So how a fundamental theory will have applications in technology, nobody knows. right? I'm not saying that string theory will ever have an application in technology, but maybe 500 years from now it will have, right? Who knows?
Right.
So yeah, so that's the way it is.
Maybe your grandchildren see that.
I mean, forget about even string theory, right? Even Higgs particle, which has been experimentally measured, will it ever have any application in real life? Right? Nobody knows, right? So far, nobody can think of any application of Higgs particle in technology, but it may happen.
So while string theory don't have any practical applications yet, but I think quantum field theory and quantum mechanics do have practical
Certainly,
applications.
yeah.
So like if we can talk about that and true power and potential of quantum computers. I was talking to Professor Kumar and he said we are going to develop a quantum city around the ICTS campus. So if we can talk about this quantum mechanics, quantum field theory and practical applications of it.
Yeah, certainly quantum computers, if they ever get built, right, it will have certainly practical application. But even without that, right, even lasers work on quantum principles. Right? Lasers certainly have a lot of practical applications. Right? You will not get lasers from classical principles. So quantum mechanics, I would say, is everywhere. Right? Semiconductors work on quantum principles.
My cameras and lot of things that we see in a day-to-day life.
Yeah, many things now use quantum principles, right? I mean, we don't realize it, but so I would not say that even quantum mechanics there is any need to justify, right? Almost everything that we use probably works on quantum principles.
So, just a personal question. So, could we ever build a computer powerful enough, to simulate our own universe?
I don't know. It seems unlikely because our own universe certainly will have more degrees of freedom than anything that we can build. Right? But maybe we can simulate things that we want to know about our universe. Right? Many things about our universe maybe we don't want to know.
Right. Or like?
Meaning, what is happening in some star, some far away part of the world. Right? Maybe we don't care.
But it would be curious to know that what is happening there.
Yeah, but if you want to simulate our own universe, the full universe, right? Full universe is also quantum. Right? So we need that many degrees of freedom. Right? So which means we need to make the whole universe into a quantum computer.
Right.
Which in a sense it automatically is. So I wouldn't say that we can simulate our whole universe in a quantum computer. But you decide on what you want to know. Right? And that you may be able to simulate on a quantum computer.
Okay. So Professor Sen, I was just when reading about these stuffs and doing my homework. So I eventually came out to be one of the most confused men. To be honest, about a lot of theories and lot of things. So I was just thinking about basics of it. I think most of our minds are actually evolved to understand classical physics. On the other hand, when you talk about quantum physics or string theory, these are not very intuitive. So how to visualize these stuffs. I was just thinking about it, how to visualize it or just think about it mathematically. So
yeah, I think most of this we think mathematically, right? That's why mathematics is such a powerful language that you don't have to visualize things always, right? In quantum theory, for example, right, there are many interpretations, but there is only one Schrodinger equation, right? And that's all that matters. That once you write the equations and you design some experiment, those equations tell you what the outcome of the experiment will be.
Sir, but I was talking about our minds are trained that way from our we don't get that early exposure.
Yeah, that's the reason that we don't try to visualize quantum mechanics, right? As you said, because our minds are trained that way, not just because of our training, but our world is mostly classical, right? So it's ingrained it's probably ingrained in our genes that we don't think in quantum language.
So how do you do that? I can't think beyond 3D. And when you talk about string theory,
so you also can't think beyond 3D, right? Okay. So when you do, say, 9-dimensional space, we write equations. Right? Okay. It's like in 3D space, we have coordinate geometry, right? So what is a 3-dimensional space? That to specify a point in space, you need 3 coordinates, right? You need its height, then its distance along the x-axis and distance along the y-axis, right? Similarly, 9-dimensional space, you visualize as you describe as something where specifying a point requires 9 coordinates, right? Once you describe it that way, then you can write equations, right? Instead of writing x, y, z, you write x, y, z and then 6 more variables, right? To specify the coordinate of a point. And then you can deal with 9-dimensional space by writing equations for those variables. Right? That's always the way. Maybe some people can visualize 9-dimensional space, but certainly not I. And most string theorists also cannot visualize 9-dimensional space. But they don't have to. Right? That's the point. That's the part of mathematics that while it may help if you could visualize, right, more than what you can grasp, but it's not necessary that you can use mathematical formula to describe things that you cannot visualize.
So you purely think in terms of mathematical equations for string theory and for your work?
Mostly, yeah. For me, certainly that's the case, right? But again, different people have different ways of doing things.
Okay.
Right. Some people think only mathematically. Some people think only physically. Right. So I think the string theorists also have a very wide spectrum that different people work different ways.
So there is one question from my friend. It is not my question.
Okay.
So he asked, in Advaita Vedanta, tradition of Indian philosophy, there is a concept of Maya, the idea that the physical three-dimensional world we experience every day is an illusion. And beneath that, there is a Brahman, a single, unified, formless, infinite reality. When you look at mathematics of string theory, do you feel that resonance of ancient idea of Maya in our daily experience of reality, just a lower dimensional projection of much deeper hidden truth? If you have any thoughts about it.
Yeah, I don't know meaning. It's very vague. It's so vague that it's very hard to make connection, right? That's why I said that, words are not enough, right? If there is an equation, then I would see whether there is any connection of what we know in string theory, right? But just by saying that what we see is Maya, I don't know what it means, right?
So actually, in India, many people try to connect everything to old books, and they get some pleasure out of it. So I just asked you for that.
Yeah. So my answer to that will be okay. If the ancient Indian scientists really knew more than what we do today, or maybe they knew as much, right? What result did they have for the ratio of the muon mass to the electron mass, right? That's a number, okay, that we know today in certain with certain degree of accuracy. Is it there in the ancient Indian text? If there are some numbers, right, that one can compare, then one can say whether they knew what they're claiming they knew, right?
Right.
So, but there is no number to compare it, right?
So talking about just general research and scientific temperament. So were we anciently rich enough in our past? If you have any thoughts about it.
No, certainly there are many Indian mathematicians, right? Ancient mathematicians who did a lot of work.
Yeah, like Pingala, even.
Madhava, for example,
right.
Brahmagupta, right? They did a lot of work. So certainly that it's not that, and their work is recorded. We know what they did.
Right.
But just by a vague statement that we do everything that in the past, right?
Yeah.
Makes no, it doesn't help anybody. It makes no sense, because if we knew everything in the past, then give me some numbers, right, which you can compare.
Right. So talking about current context, how we are doing in terms of our academic research as a country, talking about the whole temperament of the country. You came back to India, you took that plunge. So why did you come back to India?
Well, somehow I always wanted to come back to India. Right?
Come back for?
I think just no reason. I never thought of staying abroad, right? So I think it's just like as I said, I went into physics by random walk, right? I think I came back to India also by random walk. That I never thought that I'll stay there in the West. And because I was working in theoretical physics, I knew that it is not that much of a disadvantage to be back in India.
Right. So we don't need that many equipments.
Exactly.
We need that for applied physics and those stuff.
Exactly. Yeah. Okay. So for theoretical physics, that was the advantage, that I knew that there will be some disadvantage because I'll get to see the papers later and so on, but not that I'll be.
Yeah, that was, I think, pre-internet era.
Exactly. Yeah, that was pre-internet era. Right. Fortunately, internet came within a few years. Right. So even that disadvantage went away.
And what kind of peer group you had in India, to discuss stuff, you discuss and then you came out with new idea or.
Yeah. So we had a good group in Tata Institute. I first came back to Tata Institute in TIFR, and then we had a good string theory group. Like Spenta Wadia was there, he is next door. I don't know if you have met him.
And I'll meet him.
Okay, yeah. And then Sumit Das, he was a classmate of mine in college. He also had joined Tata Institute. Sunil Mukhi was there. So we had a reasonably big group.
And talking about current context, how we are doing in terms of our research and as a country, in terms of our scientific temperament and doing some very good basic research, fundamental research, how we are doing in terms of that.
Okay, I cannot say about the whole field, right? Because I don't really know. But I would say in string theory, I think India is doing reasonably well, right? Maybe it could do even better. But a lot of results in string theory have come from India.
Yeah, even I, so many legendary scientists are from India in string theory, and we have many in the ICTS too.
So yeah, and then TIFR also has many.
Right. So, Professor, in this AI era, how research and everything is going to change. Even Sam Altman said, AI will do most research in future with AGI and fast models, unparalleled information. As a human, we have a little set of information, but AI can have whole set data set and everything. So how this is going to change research? And as a human, as a basic physics researcher, this is question mark from my friend who is doing PhD in physics. So how it is going to change research, and how what kind of human creativity you can see in future with AI?
Yeah, okay. I don't know how it will change, right? But if AI can solve the problem of quantum gravity, I'll be very happy, right? I mean, if that means I know what the answer is, right? Doesn't matter who has solved it.
Right.
Till AI has solved the problem of quantum gravity, I have something to do, right? So I'll be occupied with in my research. So that's my philosophy, that you make use of AI, right? Use it as a help, right? Maybe it will eventually do better than humans, right? But till it actually has, in my field at least, right? Till it has actually solved the problem of quantum gravity, we have to keep pushing it.
And what would you like to say to young researchers who are joining physics and doing research? How do they look up to AI?
Yeah, I think they should make use of AI. Right? Right now, what are my experience is that AI still cannot do what humans are doing. Sometimes it can produce results, right? But it needs human intervention. And it's not clear whether that will go away at some point. But my feeling is that it will still be some more time before that happens, and there is still a lot of things to do for humans.
So, do you use AI in your day-to-day life in terms of calculating or any?
Yeah, I use AI. I use AI quite often. I mean, to get information. Also, some solving some problems. I've used AI. Right,
Great.
and sometimes it's useful because it has given me very useful results. Right? But sometimes it gives also complete nonsense, that it claims something which is not true. Right? So AI is like just another tool, right? You have to make use of it.
Great. And there is one more question. What role does ego play in scientific discovery? So when you work on some problem for years, a scientist should have that arrogance toward that thing. Okay, I should be the one who should do it, or just have a humility to accept maybe I am in the wrong direction, or.
No, I think you have to have the confidence, right? And you want to be the one to do it, right?
Right.
I mean, eventually it may not happen that way, right? But otherwise you will say, okay, somebody else will do it. Why put so much effort in doing it, right? So ego certainly plays a role, right? I'll say even more that one says the scientists are rational, right?
Right.
It's not the scientist is rational, because sometimes you have to have an irrational belief in something that it will work, right? Even though the current evidence may point to it's not working, right? Science is rational, right? Ultimately, if you have gotten a result, then science, whether it's correct scientifically or not, there is a completely rational decision. Okay? But often scientists have to have some irrational belief in something to be able to put their whole effort in it, right? Even though at that point of time, right, evidence may point against it.
So has it ever happened with you, you were working on some problem for many years and then you're like, okay, I am frustrated, or someone else has figured out something. So
often, of course, you work on something which doesn't work, right? That happens very often, right? So I'd say that only a small percentage of things that you actually work on eventually succeed.
Right. So have you that patience, in terms of are you very patient with things and people?
Yeah, I think you have to be patient. Yeah, I mean that's probably one of the.
So that is the problem with this younger generation, people want that instant validation and instant solutions.
Yeah, that doesn't happen in science, because this is one advice I give to students, that the in theoretical physics particularly, right, probably 80% of the time you are completely stuck, nothing is happening, right? Only 20% of the time things move, right? And when it starts moving, it moves fast, but then you are again stuck, right? And you have to have the mental strength to survive those 80% of the time, right? When you are actually stuck, and you have to have the patience and agreed to go through that period.
Right. So I'll take like, couple of more questions. So like, what is any questions or anything that you think like, science may never be able to answer? Very nuanced question, but
Questions which whose answers cannot be measured, right?
Okay.
Science may not be able to answer. It's like in quantum mechanics. Whether the many world interpretation is correct or the Copernican interpretation is correct, science may not be able to answer.
Yeah.
But this is a question you cannot even decide experimentally.
And
In principle, anything that can be measured, I would say science should be able to answer.
okay. And like, this is a final question. What is the most beautiful idea in physics for you? Not necessarily your own, that you find it very beautiful.
I would say general relativity certainly is an idea which is very beautiful, that the fact that gravity comes out of space-time geometry.
So who sort of inspired you as a physicist? Like, someone who used to look up to like, okay, this is my idol, or like, someone who inspired you?
Yeah, I don't know whether there is one specific person. As I said, when I was young, then Bose and Saha were the names we all knew.
Right.
Einstein, of course, we all knew, right? But Bose and Saha were closer to home, right? So that was probably one of the reasons why, as I said, physics was the thing to do, right? For example, when I went to the college, 5 of my classmates were among the top 10 in the board exam. So in the West Bengal board exam, among the top 10 rank holders, 5 came into physics, and they are my classmates in the college. So it was that popular. And the fact that we are local scientists probably helped. That because society valued being in science.
And like, how physics can help, like, lot of people, like Elon Musk really talk about this, like, with physics, if you study physics, you can just reverse engineer things, you can understand a lot of things in life too. So like, apart from scientist or researcher, like, how studying physics can be helpful to people like me. If you can talk about that.
Yeah, I think it helps in the sense that it helps in thinking rationally, right? That physics, the way it works, that you have some set of postulates. Based on the postulates, you make deductions, right? And those deductions you then verify experimentally, right? So the fact that there is a logical reasoning, right, that can explain many things in the world. Today, maybe we can't explain everything, right? Because science is not complete, right? But many things that you see have logical reasoning. This probably is what is important, right? And this can be conveyed even to the general public, that things have explanation, right? And those explanations are based on some standard rules, right? It's not that you decide that you write a theory and that is it, right? The theory also has to have logic, right? It has to be based on strong mathematical principles.
So if I need to start, like, learning physics, like, where I should start, if you can recommend 2-3 books or something like that.
Okay, the point is, I'm from the old days when you learned from Leslie and Halliday, right? The undergraduate physics.
Okay.
But now there must be other books, right?
I think Technicality is still very relevant, sir.
Okay, yeah, maybe. Yeah.
Yeah, I saw that book. It was that thing, I think.
Yeah.
So
And then Feynman lectures, they are very inspiring, right? His lectures on physics.
Right. Great. So definitely we'll give it a try. And thank you so much for joining us and giving us a lot of learnings, insights, and making me understand a lot of things. So thank you so much for that.
Thank you very much.
Thank you.
Thanks.